What if one man could look at an apple falling from a tree and see not fruit, but a law that ruled the entire universe? That's exactly what Isaac Newton did, turning ordinary sights into extraordinary truths. But his story isn't just about apples and equations. It's about secrets, rivalries, obsessions, and a lifetime wrestling with mysteries as big as space and as small as light. By the end, you'll understand why Newton didn't just measure the cosmos. He changed what it means to measure reality itself. How could a sickly, fatherless boy in a quiet English village grow to become the world's greatest scientist? The answer begins with a body so frail that few thought it would survive. Born small, weak, and already marked by loss, his first breaths set the tone for a life shaped by struggle. He entered the world in Woolsthorpe, a farming village of stone walls and muddy roads, far from the centers of power or learning. Nothing about his beginning hinted at greatness, yet history would prove otherwise. His father was already gone, leaving the child without a male figure in a household where survival depended on strength and land. His mother carried her grief and uncertainty. She had a small farm to manage, and her son's fragile health made even simple care precarious. Imagine a baby so underweight that neighbors whispered about his chances, a child who might vanish before his name was even remembered. That uncertainty formed the first backdrop of his story. Isolation arrived early. When his mother remarried, she left him behind with his grandmother. For a boy already used to silence and weakness, this was another fracture. His home became one of absence as much as presence. Instead of the lively bustle of siblings and parents, his days were filled with solitude, with fields stretching beyond the window and tools scattered across the farmyard. His companions were not people, but objects, books left on a shelf, bits of wood or metal, and the odd instruments that could be taken apart. This separation mattered more than comfort. Psychologists looking back can see how early childhood deprivation often shapes certain kinds of minds. When connection is withdrawn, imagination steps into the gap. Curiosity feeds on loneliness, and ritual or obsession becomes a source of stability. For Newton, this kind of environment stamped itself into his habits. He would spend hours alone, building small contraptions, scribbling his thoughts, watching how shadows stretched and objects fell. A child deprived of family closeness found rhythm in studying material things. Picture him, a thin boy in plain clothes, crouched over a crude notebook by the light of a small window. Outside, his peers carried pails or dug in the soil. Inside, he was dismantling locks or sketching odd symbols, trying to see how the pieces worked together. In a place where survival meant planting and reaping, he planted questions instead. Even without guidance from teachers or elders, his mind sought order, as if looking for a substitute for the order missing in family life. The lack of affection did not limit him. In fact, it may have deepened his drive. Research in human development often shows how early adversity builds resilience, but in some rare cases it fuels a kind of relentless inward turn. Newton became one of those rare cases. His world shrank to himself, his tools, his questions. Books were his allies. He consumed scraps of knowledge like a starving body takes food piece by piece, sentence by sentence. What he lacked in mentors or classmates, he replaced with diligence. Other children played in groups, forming alliances and rivalries. Newton sat by himself, recording the flight of birds or the mechanics of a water wheel he had rigged from spare parts. He learned not by instruction, but by relentless trial. Each mistake or malfunction was met not with shame, but with deeper concentration. Failure became part of the process, a private process, shielded from the judgment of others. This inward focus also scarred him. His later life, filled with secrecy and suspicion, likely carried traces of that childhood wound. Trust was not natural for him, Dependence on others seemed dangerous because people could leave, objects could not. A compass could be studied again and again without betrayal. A prism would bend light, whether one was loved or abandoned. Nature was the constant his family never provided. His connection to his mother remained strained. Reunions carried tension, reminders of absence, and of her new household where he did not belong. That pattern may have prepared him to resist authority later in life. Challenges from rivals, dismissal by critics. These did not crush him, because since childhood he had lived apart from approval. Recognition was never fuel. Curiosity burned on its own. It is striking to think about the contrast. Out of a small, quiet village surrounded by sheep and farmland arose a mind that would one day redefine the movement of planets. Out of early abandonment and frailty came a man whose equations would last for centuries. The seed of greatness often begins hidden, shielded by pain. He carried with him the qualities of solitude, focus, endurance, the very tools needed for original discovery. Let's pause for a moment with that frail boy, one who shaped toys into machines and scratched diagrams into margins. If you were standing in his small chamber, you might not see a future scientist. You might only see an undernourished child, quiet and reserved. Yet this was the same child whose thoughts would one day connect falling stones with the arc of the moon. And the habits forming now, long hours of silent study, refusal to accept second-hand truth, would become the foundation of his success at Cambridge and beyond. Neuroscience today suggests that the brain under stress often learns to focus narrowly, filtering the world for patterns. In Newton's case, this narrowing became a strength. He mastered attention. When he looked at a problem, he could hold it in his mind like a craftsman gripping a tool, turning it again and again until he wore it down to its essence. That endurance began as a coping mechanism in childhood and matured into his method as a scientist. We see here why his hardship was not simply a barrier, it acted as a forge. The absence of ordinary warmth left him hungry for structure, and structure he sought in nature's laws. His fragile birth gave him reason to value survival, and survival demanded vigilance. His separation from family freed him from community expectations, making him less bound by custom when questioning authority later in life. So the fragile boy in Woolsthorpe was not destined to fade. He was bound instead for persistence. Every weakness became a counterweight, pressing him harder into study. Every loneliness became a teacher. The simple tools and books of his youth primed his mind for discovery in a way no formal training yet could. He absorbed early wounds and turned them into patterns of work that would one day expose the hidden forces holding the universe together. From this obscure farm, the path extended outward. It would carry him from solitude to Cambridge, into halls filled with ancient texts and debated principles. There, the boy who once watched shadows lengthen over fields would challenge the greatest traditions of learning. His childhood had already prepared him for it. Isolation had trained his focus, frailty had sharpened his endurance, and abandonment had taught him to trust only in the visible, testable order of things. His journey from fragile child to scholar, waiting at the threshold of revolution, began here, in the silence of Woolsthorpe. From there his path bent steadily toward the intellectual heart of Cambridge, where the questions buried in him since boyhood could finally take shape. What if the deadliest event of his generation forced Newton into the most productive year of ideas in history? Imagine a scholar at the edge of his studies, faced with the closure of every hall, every library, every crowded street. For most, disaster. For him, the beginning of something no one could foresee. When Newton first entered Cambridge, he stepped into a world steeped in tradition. Students pored over Aristotle's writings, centuries old, still treated like maps of reality. Descartes had begun to stir thought toward a new science of motion and mechanics, But the air of Cambridge was heavy with reverence for ancient texts. To many it was enough. You memorized, you debated, you repeated. But Newton was restless. He saw the structures built by older thinkers, yet the answers felt hollow. How did bodies move, not in words, but in exact measure? Why did light behave as it did, bending, scattering, blazing in the sky? The old explanations seemed like scaffolding around an unfinished house, impressive but empty inside. Now place that hunger against the backdrop of plague. Disease crept across towns. In streets, carts hauled away the dead. The danger was invisible yet undeniable. Entire households fell silent. In some places, goods from infected homes were burned in the hope that fire might purify what medicine could not. Cambridge, like every gathering place, saw the risk multiply. The university did what it had to do. It closed its doors. For teachers and students alike, this meant exile. Work was disrupted. Routines vanished. Newton, still young and not yet tested, journeyed back to Woolsthorpe, the same rural setting where his frail childhood had unfolded. For many, this would have been a return to nothing. No lectures, no peers, no access to manuscripts or debates. It might have been wasted time, where ideas lay dormant. But in his solitude, something different happened. Cut off from professors, spared the burden of exams and schedules, his mind became its own university. What changes when you remove a structure of authority? Suddenly the page is blank. Newton's notes from this period revealed a shift. He was free to follow his discontent with Aristotle into calculations of his own. In mechanics, he began sketching lines of thought about motion. He asked how change could be pinned down not by vague terms, but by symbols, procedures, quantities. Out of this search, the early outlines of calculus appeared. He was not ready to publish, but the concept was there. A language to capture motion step by step, to measure the curve of a path, the surge of speed, the area under a line. His experiments were not limited to symbols on paper. He took up prisms, tools, sunlight. In darkened chambers, he forced a narrow beam through glass and watched it spread into color. Conventional thinkers claimed white light was pure, that color was a distortion imposed by the prism. Newton saw the opposite. That color was already within, and the prism revealed its composition. It was an insight, grown not from group instruction, but from private persistence, unchecked by the currents of opinion. Return for a moment to the feel of that environment, isolation outside, silence within, the air punctuated by news of death across the countryside. This was not a college filled with debate. It was a farm where a solitary figure scribbled notes and adjusted angles of glass. Crisis had prized him away from conformity, and the absence of noise became material for discovery. Among his most remarkable leaps was a thought as simple in seed as it was vast in consequence. Consider a body falling. Consider the moon. Might the same force guide both? The apple falling to the earth and the moon pulled toward us in orbit. Were they motions of different orders or of one? That question's shape appeared during this retreat, though its final form would take years. Even so, the link began here, an orchard, a quiet sky, a mind piecing falling fruit together with the orbit of worlds. Step back and see the pattern. Over the course of about 18 months, Newton achieved what others might not in a lifetime. He had a framework for calculus, an experiment overturning assumptions about light, and a direction for a law that could bind heavens and earth. It wasn't Cambridge that gave this to him. The plague stripped away distractions and left only the elements of thought, question, observation, calculation. What most feared as ruin became, in his case, a release. Think of it like pressure in a sealed vessel. The more confined he was by solitude, the more concentrated his energy became. Without the outlets of public debate, all motion turned inward. energy condensed in calculation rather than conversation. Each problem became an obsession, each experiment an anchor in a world suddenly emptied of contact. If you were there in Woolsthorpe, you might have seen nothing remarkable. A young man sketching in notebooks, tinkering with glass, walking the fields and stopping often as if distracted. To neighbors, perhaps eccentric. To history, a mind recalibrating the world. The harsh reality of disease, the broken rhythm of education, forced him into conditions that appeared barren. Yet barren space often breeds the most striking growth. And this is the strange irony. The plague, which cut down lives across nations, extended Newton's reach across centuries. It severed him from Cambridge, but gave him something purer than lectures. Time, freedom. The chance to pursue questions no one else had framed with such precision. Instead of being crushed by crisis, his work accelerated under it. We often think of invention as teamwork, as collaborative rooms full of exchange. Newton demonstrates the other side, the power of solitude sharpened to its limit. Crisis did not give him answers, but it created a chamber where his questions reverberated until they found their form. That is why historians sometimes call this span of months his year of wonders. Calculus, optics, gravitation, three foundations, all germinating at once, all seeded in enforced retreat. So when we trace the arc of modern science, we must stop here, in that farm, in that silence. Because this moment shows us how disruption can paradoxically give rise to renewal. Plague emptied the schools, but it unclogged the river of thought. With no professors to please, Newton pleased only his own relentless drive. In just 18 months he redrew mathematics, reframed the study of light, and began to imagine a force that governed the entire cosmos. You could call it luck, but that word ignores the training already laid in his childhood solitude and the discipline refined through hunger for knowledge. Crisis fused with character, and out of that fusion came some of the greatest advances in human thought. A retreat meant for survival became nothing less than a launch pad, one that sent us from the orchards of Lincolnshire into the framework of the modern world. Did Newton really see gravity in a falling apple, or is this just a myth? The story has been told and retold so many times that it feels closer to legend than memory. Yet, when we strip away the embellishment, an apple still sits at the heart of it. The one account closest to Newton himself comes from his friend William Stukely. In his memoirs, Stukely recalled Newton telling him how he observed an apple fall while he sat in quiet thought. That moment of fruit dropping to earth, ordinary to most of us, pressed a question into Newton's mind that was anything but ordinary. We all know apples fall. It doesn't surprise you or me. The tug of earth pulls everything downward from pebbles to branches to ripe fruit. But think about what it takes to pause at such a sight and ask, why? What is the underlying pull that sends every object earthward? And could the same force stretch beyond our orchards? Newton looked at something simple and saw a puzzle open across the sky. The challenge is clear. An apple is small, predictable. Its fall is quick, measured in a split second. The moon, on the other hand, hangs far above, gliding endlessly around our planet. How could those two motions belong to the same rule? To the average observer, they belong to separate worlds, fruit in a garden on the one hand, celestial bodies on the other. What Newton managed was a leap not of sight, but of thought. He built a bridge between the ordinary and the immense. Picture him sitting there, the orchard around him, silence except for the thud of a fruit touching the ground. In that quiet he asked himself, if the apple falls because earth pulls it, then what keeps the moon from falling? The answer he began to form was startling in its simplicity and its scope. The earth does pull the moon, the same way it pulls the apple. The moon falls constantly, not downward onto soil but sideways into orbit. It circles because its forward motion combines with Earth's pull, keeping it in a loop rather than a crash. This is where an analogy helps. Imagine swinging a ball tied to a string. The string pulls inward while the ball tries to fly outward. That balance creates a curve, a circle. In Newton's eyes, gravity played the part of the string. The invisible tug holds planets just as surely as it brings apples down. Suddenly, orchard and heaven seemed part of a single fabric stitched by one force. We might ask, was the apple really the cause, or was it just a moment he used later to paint the story? Accounts suggest Newton himself mentioned it to trusted friends in later life, and Stukely wrote it down after Newton's death, recording the memory as Newton had told it. Even if the story has softened into fable, the link of falling fruit and falling moons represented his real thought. The symbol lasts because it captures the power of curiosity, seeing in the everyday something that stretches into the infinite. Let's consider why this leap mattered. Before Newton, people described motions of planets, but often kept them apart from the motions we see here on Earth. Celestial mechanics belong to realms of speculation, often wrapped in separate ideas about the heavens. Earthly falls and celestial orbits occupy different categories. By making them a single case, by seeing that apples and moons answer to one and the same pull, Newton erased the division. This was not just another theory, it was a unification. Think of it like discovering that two seemingly unrelated machines share the same engine. One machine may grind grain, another may power a pump. They look different. They act in different contexts. Yet, at their heart is one driving mechanism. Newton declared that the engine of falling apples is the engine of the planets. The orbit of Mars, the arc of a tossed stone, the drop of fruit. One law. This shift reshaped how we see our place in the cosmos. Suddenly, the heavens were not a realm of mystery following unknown rules. They were continuous with the world under our feet. What grounded apples to soil also governed galaxies. It was a leveling of sorts, a sign that laws are not fragmented. A single thread ties movement from our hands to the stars above. But remember the scale of what Newton sensed. No equations had yet been published. He was still a young thinker, filling loose notes and running private tests. The system of mechanics he would later reveal in the Principia was years away. Yet the apple story marks where thought first swelled beyond the horizon. He began to sense that the world operated under a principle wider than any yet written. The ordinary garden, with its fruit and soil and shadows, contained hints of a force that stretched without limit. This is why the story resonates to this day. It is not the certainty of the apple itself, but the clarity of Newton's question. Could the local and the cosmic, the small and the immense, be ruled by one hand? His brilliance lay not in seeing the fruit drop, but in refusing to let the sight remain trivial. He pulled out its consequence. To most people, the moment of fruit striking earth closes the event. To Newton, that event demanded explanation until it reached the moon, and when we look at what followed, we see how right he was. The law of universal gravitation became one of the cornerstones of science, guiding not only astronomy, but navigation, engineering, and the progress of physics for centuries. In this sense, the apple is more than anecdote. It is a symbol of focus, the ability to turn a fleeting second into an enduring principle. It demonstrates the process of science, observation joined with imagination, then tested against reality. By linking apple and orbit, Newton reframed gravity as universal. No longer a local quirk, it became a general law, underpinning both orchards and galaxies alike. So yes, we can say the apple story is part fact, part legend, but its truth is in the way it captures a leap of thought that reshaped knowledge. Newton was not gifted with a magical vision. He was rigorous, persistent, and bold enough to see unity where others saw separation. That unity began in a garden, under a tree, during a moment that could have gone unnoticed. From that insight, the full structure of modern physics would later rise. But before Newton committed these ideas to formal writing, he set them aside for a different mystery. He wanted to understand not just why apples fell or moons circled, but why sunlight broke into color when bent through glass. The next step of his journey carried him deeper into the strange nature of light itself. Now measure the distance we have traveled. A fallen apple in a Lincolnshire orchard leading into orbits of planets, and then onward into the spectrum of light. Newton's garden moment reframed the entire cosmos, and from fruit to star to prism, his mind kept pressing forward, hunting another hidden order. How did Newton turn a schoolboy prism trick into one of science's most revolutionary experiments? At first glance, it may appear to be nothing more than a play of light through glass, a party novelty anyone could try. Yet, in Newton's hands, a prism became not a toy, but a probe, an instrument to reveal nature's hidden structure. He pursued this not on a stage, but in a chamber barely lit, where sunlight admitted through a hole in the wall could be shaped into a single thread of brilliance. That was where the breakthrough began. Picture the scene. A closed room, shutters drawn tight. A single beam of sunlight pierces the darkness through a controlled slot in the wood, not wide as a window, but narrow enough to behave like an instrument. Newton placed a prism in the path of the beam and watched as the brilliance split into color. A ribbon stretched across the wall, marked from one edge to the other in vivid sequence. To a casual eye, a rainbow produced indoors. To Newton, evidence that the world's assumptions about light were mistaken. Most thinkers of his time would have described white light as pure. In their eyes, the prism corrupted or stained what was originally uniform. The array of colors was seen as a distortion, irregular in origin. Newton challenged that view. He held that the glass revealed, not corrupted. White was not single at all, but composite, the mixture of distinct ingredients already waiting inside. The prism only unlocked them. You can think of this in the way soup might be strained. If you believed broth to be uniform, forcing it through a filter and seeing layers appear would be startling. Newton saw something similar with light. Once split, each component obeyed rules of its own. He tested this directly. Selecting a band of red, say, and passing it alone through another prism, he saw it remain red. It did not split any further. A green beam remained green, a violet remained violet. This meant the prism had not created color. It had only separated what was already there. The precision of his method was unusual for the time. He darkened the space to eliminate stray reflections. He adjusted the size of the aperture to keep the beam narrow. He marked where each color appeared, measuring shifts in their positions with great care. These details mattered because controversy was sure to follow. His claim overturned the old understanding of purity, and with it, the pride of senior scholars. When he presented his findings, resistance came quickly. Hooke and Huygens, both significant voices, disputed his conclusions and his explanation. Hooke favored a wave-like motion for light, naturally opposed to Newton's suggestion that light was made up of particles, corpuscles fired in straight lines, bouncing and refracting like stones in water. Huygens, working with wave descriptions, raised different objections. What might have been quiet debate soon became sharp, personal rivalry. Newton was not a man at ease with dispute. Instead of engaging openly, he grew guarded. His correspondence became clipped, his sharing selective. He feared criticism, worried that his peers would claim priority or twist his results. In part, this secrecy echoed his childhood, where trust was fragile and privacy constant. But it hardened now under the weight of challenge. He withheld some of his notes, hoarding results until convinced he had proof beyond contest. Yet the prism experiment could not be denied. Even critics had to recognize the care with which he isolated each factor. His distinction between pure colors and composite white reshaped the field. The claim was not only theoretical, it explained practical problems too. Astronomers using refracting telescopes faced flaws when the lenses produced halos of colored light. Chromatic aberration. Newton's insight suggested a path forward. Remove the refracting lens from the design and use mirrors instead. From this came his reflecting telescope, a device superior in clarity and compactness and a direct application of his prism work. To the outside world, this inventive leap enhanced his reputation. But inside the halls of science, his relationship with peers strained under the weight of accusation and criticism. Hooke, in particular, pressed him, and Newton answered with increasing defensiveness. Statements grew barbed, letters terse. The seeds of rivalry planted here would linger for years, shaping much of Newton's posture toward the community of scholars. Still, in the calm of his private study, he must have seen in his spectrum a reality no one else had touched, a hidden structure lying in what people mistake for uniformity. His rainbow proved that appearances flatten differences. White sunlight pretends to be one thing. In truth, it conceals variety that must be broken apart to be seen. That was his genius, not to marvel at the rainbow as beauty, but to see it as data, as evidence of light's true composition. The analogy with language is useful. To an untrained ear, noise might seem a single blur, but careful listening, or an instrument to separate frequencies, reveals many voices inside it. Newton supplied that ear for light. He showed that a field once thought smooth was, in fact, crowded with character. Each color bent by a degree unique to itself, each refracted path confirming individuality. From these experiments, spectrography, spectroscopy, and the science of light in stars would grow centuries later. He set the trunk that future branches would extend. Unsurprisingly, his posture tightened as disputes grew. He circulated less, spoke less openly, and trusted fewer colleagues. What had begun as playful inquiry into a beam of light became a crucible where personality and theory collided. Newton's temperament, cautious, secretive, and often prideful, met the sharp tongues of rivals. Out of that collision emerged both brilliance and bitterness, progress secured but harmony lost. His prism experiments mattered for another reason. They revealed the way he approached science, not by assuming, but by building controlled setups where every condition could be checked. He distrusted second-hand reports. He trusted only what instruments, beams, shadows, and geometry gave him. In doing so, he laid a model for experimental science itself: precision, isolation of variables, demonstration repeatable by eye. Imagine standing in that chamber, a thin shaft of sunlight piercing the gloom, breaking into arcs against the far wall. The air cool, the quiet heavy, and in front of you, the spectrum of order displayed like a code. What would seem like magic at first glance is in fact a map. Newton read that map and declared light itself to be compound, not pure. A conclusion that angered contemporaries, but one that time would only confirm. In that rainbow, Newton did not simply describe color. He showed that nature hides its truths within things we think we know. White is not white. Purity is not pure. The world must be broken open to reveal what it holds. His experiment with prisms became a mirror of science itself, passing apparent simplicity through the glass of method to expose the spectrum beneath. This was the moment when light itself changed meaning, not beauty on the horizon, but evidence in the laboratory. A fundamental shift achieved not with a grand machine, but with a small prism, a darkened room, and a single beam of sun. And with it began the clash of personalities that would orbit Newton's career from that point onward. Why did one of the greatest works in science nearly never get written? The story of how Newton's Principia came to exist is a mix of conflict, hesitation, and one supporter who refused to let the work vanish into silence. What began as scattered notes in private notebooks became a book that changed the world, but only through a push that Newton himself resisted almost to the point of failure. At the center was Newton's reluctance. He had the insights, the mathematics, and the frameworks. He had already imagined a law that might rule both earth and sky with the same grip. Yet past experience had taught him what criticism felt like. Accusations of error, claims of stolen ideas, arguments carried in letters that turned sharp and personal. He had endured this during his work on light, and he hated it. For Newton, every public dispute was a wound. To protect himself, he built walls of secrecy, hiding his work away. Robert Hooke's role made matters worse. Hooke put forward that the force-binding planets might follow an inverse square relation, weaker with distance, but never-ending. For Newton, this was infuriating, because he had already reached that logic years before. He believed Hooke was pressing for credit, claiming priority without proof. To Newton, that was unbearable. He wanted certainty. He wanted ownership. The idea that others might think him derivative only deepened his silence. Then came Halley, a man who saw the value in what Newton had written and who knew persuasion alone might not be enough. Halley recognized that Newton's ideas, locked in drafts, were not just theories, but a system that could unify motion across scales. That system deserved publication. He visited, pressed, encouraged. Without Halley's persistence, Newton might have continued to let the work rot in secrecy, a treasure buried out of spite. Tension built. Newton had calculations spread across messy pages, symbols scratched in trembling strokes of ink. In those notes were the foundations of his 3 laws of motion. First, that a body resists change, carrying on in a straight line unless acted upon. Second, that change in motion follows in measure to the force applied, a link between cause and effect captured in numbers. And third, that every push carries its equal push back, a symmetry governing every interaction. These principles, clear in retrospect, were scattered in fragments for him. Bringing them into order demanded patience. He resisted offering to a public that might attack him. Halley did not just argue. He offered more. He took on the cost of publication himself. In an age when printing required a patron, this mattered. Halley reached into his own resources to ensure the book could exist. What Newton could not stomach in trust of peers, Halley replaced with material support. The pages began to be set, not because Newton chased fame, but because someone else bore the burden. The process was not smooth. Hooke's claims hovered, reminders of rivalry. Newton responded with hostility, narrowing his social circle further. He allowed drafts to circulate only under strict control. At one stage, there was risk that quarrels would derail the project, that Newton's temper would win, and that he would withdraw everything again. That possibility lingered until printing began. Even then, Newton revised obsessively, extending the work into multiple books, stretching effort well beyond Halley's budget. Picture those manuscripts, equations sprawled along the margins, geometric proofs stacked across pages, diagrams connecting the orbit of planets with the fall of stones. It was a mental bridge laid out in ink, bringing together the movement of the smallest objects with the paths of the largest. Planets became predictable as projectiles. Apples linked to moons, the arc of a stone echoed in the ellipse of Saturn. For the first time, one book promised to connect them seamlessly. The heart of it was universal gravitation, a force acting at a distance, declining by the square of the distance, constant throughout. The same pull that drags fruit down is the one that bends Jupiter's moons in their tracks. This idea was radical because it united what had been separated. Earthly falls and celestial orbits were not divided realms. They were parts of one universe ruled by one rule. Think of it like discovering that tides, river currents, and ocean storms are all manifestations of one water cycle. What had appeared isolated now belonged to one system. As word spread after publication, reactions were mixed. Some greeted the insight as revelation, others clung to older views or questioned elements of Newton's methods. Criticism remained, and Newton's distrust of rivals grew sharper, yet the larger consequence became clear. The Principia offered a framework, a structure of reasoning strong enough to support generations of investigation. It was not just another scientific book, but an anchor for classical physics. To this day, we see why. Those three laws of motion still describe the everyday with remarkable accuracy. Why wheels keep rolling until friction halts them, why engines push vehicles forward, why rockets expel gas to climb skyward. The connection of action and reaction, of inertia and force, remains embedded in engineering, mechanics, and even the way we teach children to push swings. These are daily echoes of what Newton folded into careful Latin prose and dense geometric proofs. What Halley's encouragement and funding secured was not only Newton's reputation, but the usable skeleton of modern science itself. Without that push, the Principia might never have left Newton's desk, stranded as private calculations. Instead, it became the reference text of its age, studied and debated across Europe, shaping navigation, astronomy, engineering, and philosophy. Its weight extended far beyond mathematics, pressing into how people understood order in nature. Consider again why it was almost lost. Newton's paranoia, Hooke's challenge, the fear of criticism, the bitterness of rivalry, and the absence of funding. At each stage, the project could have collapsed. The fact that it did not is as much the work of Halley as of Newton. That partnership, uneasy but essential, carried theory into permanence. The result was a volume often called the Bible of Physics. To open it was to find not only the statement of laws, but the demonstration of a method. Deduction from principle, confirmed by observation, explained with clarity. It showed how to reason with mathematics about the natural world. It told scholars that nature is lawful and that law can be written down. When we hold on to this achievement, we also see the irony. The man who most resisted exposure gave the world one of its greatest exposures of truth. The reluctant author ended by producing a book that still stands as a landmark in human thought. And yet, Newton's story did not close with theory. His mathematics and physics remained central, but soon his attention shifted beyond academia into matters of coins, crime, and authority. From cloistered scholar, he emerged as an unlikely figure of power in the machinery of a nation. Why would the world's most rational scientist fill notebooks with coded symbols about turning lead into gold? At first glance, it feels like contradiction, as though logic and mysticism sit side by side at one desk. Yet inside Newton's study, stacks of handwritten pages prove this was no side project. He copied texts by ancient alchemists, added marginal notes, drew elaborate charts, and layered them with secret symbols. Thousands of pages survive, each crowded with instructions, ingredients, and coded reactions. It was not casual curiosity. It was intense commitment. In Newton's day, alchemy carried both attraction and danger. Some saw it as the key to unlocking the deepest forces of matter. Others dismissed it as superstition, unworthy of serious thought. For Newton, it fit neither category cleanly. To him, it was natural philosophy in disguise. He believed that behind the arcane symbols, behind the riddles of the philosopher's stone, lay hidden rules of transformation. Alchemy was not about fantasy. It was about discovering a deeper order. Imagine that study lit only by candle flame. Wax dripping on the desk, smoke curling upward, glass vessels arranged in careful formation. Newton spent long hours there. He heated metals until they glowed. He mixed powders and liquids in combinations that risked violent reaction. Mercury, sulfur, saltpeter, substances we now know hold serious hazards, were daily instruments in his work. On his hands and clothes hung stains. The air around him carried fumes few would endure. His notebooks record an obsession with fire. He treated flame not as destruction, but as key. Fire separated, purified, and revealed. Through heat, a base metal might lose its form and assume another. If metals could change, perhaps nature itself held a principle of unity. Each operation he attempted, every alloy he formed, hinted at levels of transformation still concealed. For Newton, this was not a distraction from science, but an extension of it. At the center of alchemical tradition stood the idea of the philosopher's stone, a substance that could transmute one element into another. In legend, it yielded gold from common matter. In Newton's notebooks, it became a symbol of possibility. He copied recipes for its preparation, diagrammed retorts and furnaces, and encrypted observations so that only he could decipher them. What to the outside world might look like an impossible dream was to him a structured investigation. Matter concealed mysteries beyond current knowledge, and he believed careful trial might one day uncover them. We should place this in its wider moment. The 17th century blurred the boundary between science, religion, and esotericism. Robert Boyle, known for work on air pressure, also wrote about alchemy. Hermetic texts circulated, promising ancient wisdom hidden in coded form. In this climate, Newton's work was not entirely out of place. The difference was the depth. He pursued alchemy with the same intensity he gave to mathematics, not as idle speculation, but as rigorous effort, page after page of method and symbol. The secrecy of his alchemical studies was crucial. To reveal such practices openly could invite ridicule or worse. The scientific establishment, already wary of untested claims, treated alchemy with suspicion. The Church often viewed it as heretical, mixing human ambition with sacred mysteries. Newton kept his manuscripts private, rarely discussing them even among peers. The coded language, obscure references, and deliberate concealment all show caution. He built walls around this part of his life. Why endure the risk? Because to Newton, alchemy offered a bridge. He saw in its strange recipes hints of a unified cosmos where matter is not static but dynamic. If metals could transform, then perhaps every part of nature hid a process of transformation. Alchemy's goal of turning base to precious mirrored a cosmic principle, order built from hidden rules. He believed these secrets were steps toward a fuller picture, where the physical and the spiritual met in law. Think of it in analogy. Imagine trying to understand a machine by watching only its surface. Alchemy was Newton's attempt to look under the casing to find gears and springs beneath. The old texts, obscure and symbolic, were like blueprints written in riddles. He copied them, hoping repetition might reveal pattern. He tested compounds, hoping fire would show transformation. Each effort was a probe into the hidden structure of matter. The physical risk was real. Mercury, in particular, left stains on his notebooks, evidence of direct handling. Exposure to its fumes could damage health and mind. Yet he persisted. Experiment required danger. He was willing to sacrifice comfort for glimpses of nature's secrets. His commitment shows not only curiosity, but also the intensity with which he pursued truth, regardless of cost. Historians today read his alchemy with caution. Some see it as error, a sideline where genius lost itself. Others argue it influenced him deeply, guiding the way he thought about forces and matter. The truth likely lies between. His search for unity in alchemy echoes his search for unity in gravity and optics. He wanted one set of principles linking the falling apple, the colors of light, and the transmutation of elements. To him, all these belonged on the same map of creation. The philosopher's stone, in this reading, was less about gold than about knowledge. It symbolized transformation, both material and spiritual. To find it would mean uncovering the very order of matter itself. For Newton, steeped in theology as well as science, that order pointed toward design. Alchemy became a means of reading the hidden script by which nature was written. Close your eyes and return to that small room. Shelves lined with bottles, diagrams inked in tight script, the air thick with heat and metallic smoke. The rational master of mathematics coexisted there with the seeker of mystical secrets. One side calculated the orbit of the moon. The other searched for a substance that might never exist. Together, they formed a whole. Newton's notebooks in this domain remained unseen for centuries, packed away, dismissed, or ignored. Only when opened did scholars grasp the sheer volume, thousands of pages, written not as fancy, but as careful work. That hidden archive reminds us that genius does not always walk a straight line. It wanders, it circles, it crosses into shadows before returning to light. His alchemical pursuits may surprise us, but they reveal the depth of his conviction that nature is layered with hidden law. Whether through mathematics, prisms, or crucibles, he sought that law. Alchemy was another tool, no less than calculus or geometry, though its results proved less enduring. What it left was insight into the mind of Newton, a man unwilling to leave mysteries untested. The balance of his life shows both extremes, rigorous proof and secret obsession, cold reason and heated experiment. His alchemy did not undermine his science. It showed how broad his hunger truly was. He straddled the line between what we now separate as science and mysticism. Any complete picture of Newton must hold both. In the end, these hidden obsessions remind us of the strange blend from which discovery often grows. Genius walks with both light and shadow. For Newton, the quest to understand gravity sat beside the quest to transform matter. Both were chapters of the same search, to see the hidden laws of creation. Even in his faith, he would challenge orthodox belief. The same secrecy that guarded his alchemical papers also covered his theology. And there, too, he saw a universe filled with order, designed yet mysterious, waiting to be understood. How could a man redefine science yet secretly doubt the core tenets of his religion? Newton's reputation rests on universal gravitation and the laws of motion. Yet if you step into his private world, you find an equal, perhaps greater, weight of words devoted not to physics, but to Scripture. He wrote tens of thousands of words on the Bible. He traced prophecies, timelines, and coded patterns as if the universe's laws were buried there, waiting to be uncovered by patient reading. His Bible was not a passive book for prayer. It became a kind of laboratory filled with marginal notes and dense systems he alone might understand. This was not fringe study nor a passing diversion. To Newton, these texts were tools of discovery as serious as prisms or equations. Page after page, he mapped chronology, trying to align events recorded in Scripture with the unfolding of history. He drew long sequences, where each moment carried meaning, where numbers promised hidden symmetry. If his work in mathematics provided language to describe motion, his work in prophecy aimed to describe the order of time. Two studies side by side, both searching for evidence that creation was rational, structured, and intelligible. But inside this devotion lay a dangerous fracture. Newton rejected the Trinity. In the Church of England, this was no small disagreement. It was the central creed, affirmed by law and by ritual, defended as fundamental to salvation. To challenge it was to step across a forbidden line. In 17th century England, heresy was not an abstract word. It could invite punishment, exclusion, or worse. Newton knew this risk. And so, where others published sermons, he remained quiet. His disbelief lived only in private papers. Those papers would never see light in his lifetime. Imagine the tension of that secrecy. On the one hand, a nation where religious authority was stitched through law, monarchy, and public order. On the other hand, Newton's private refusal to conform. Each Bible he owned became thick with annotations, notes added in cramped script, passages dissected, and verses cross-referenced with relentless care. For him, the text was narrative and code at once. He built intricate charts, sketching Christian history as a grand sequence of ages. All this remained behind closed doors. Picture a desk lit by oil lamp. An open Bible lies spread out, its margins crowded with notes. Beside it, another pile of handwritten drafts never shown beyond the room. In those drafts, Newton set out beliefs that, had they been known, could have ruined the scholar who was becoming one of the most powerful voices in science. His silence preserved his place in public life, yet his private faith kept driving him forward. The paradox is striking. His colleagues knew him as the mathematician and natural philosopher who defined the mechanics of motion. Hidden from them was the other Newton, one who treated theology with the same seriousness. For him, scientific inquiry was not opposed to religion, it grew out of it. When he described the laws of motion or the force of gravity, he did not see a world stripped of God. He saw divine craftsmanship. Mathematics was the script written into nature, and his equations were acts of reading that script aloud. Think of it this way. A watchmaker leaves the gears of a clock visible when polished. For Newton, God had done the same with creation. Every orbit, every fall, every refracted beam of light revealed structure. The rules of motion were not a replacement for the divine. They were evidence of it. His rejection of certain doctrines did not make him less devout. If anything, it pressed him harder into the conviction that the universe unfolded under a rational design. The boldest insight was that gravity itself became proof. For others, gravitation was a physical fact. For Newton, it was also a sign of order, a pattern stitched across the cosmos that could only come from a guiding mind. Apples fall, moons circle, planets sweep ellipses. None of this, in his view, could come from chaos. Law implied lawgiver. Discovery implied design. Each new proof doubled as a form of worship, showing that the same order-binding matter also revealed the Creator's hand. Yet imagine the cost of keeping so much internal. Religious orthodoxy was policed tightly. The wrong confession could end careers. The wrong sentence could erase status. Newton's caution was not cowardice, it was survival. He knew where power lay and how easily dissent could be crushed. So he wrote, he calculated, he annotated, but he did not publish. His faith lived parallel lives with his science, public acceptance on one side, private defiance on the other. This secrecy shaped his character. It trained him in caution, in the habit of keeping thoughts behind locked doors until certain. The same pattern touched his science, where experiments and drafts remained hidden until polished to the point of certainty. The larger pattern becomes clear. Newton studied forces of nature in the day and prophecies at night. He traced laws of motion for public lecture while drafting timelines of revelation for himself. To him, the two pursuits were connected. The rational structure revealed in mechanics matched the rational structure he sought in Scripture. Where theologians saw mystery, Newton sought measurement. Where priests claimed authority, he searched for law. The outcome was a worldview uniquely his own, not orthodox by church measure, not secular by modern terms, but a fusion. Science showed order, theology described purpose. Together they painted the universe as intelligible and deliberate. He did not imagine a world without God, but a world that was evidence of God in every equation and every falling stone. By grounding his science in faith, Newton gave it cosmic purpose. Laws were not arbitrary. They were signs of harmony, Proofs doubled as sermons of order. Every solution to a problem demonstrated that the universe was not fractured. From light split by prisms to orbits measured under gravity, all pointed to coherence. That coherence was to him the surest mark of a creator's design. We often imagine science and faith as opposed, but in Newton they worked as parallel engines. Theology asked him to search for meaning. Mathematics gave him the tools. Each question fed the other. The Bible was a map of history. Nature was a map of motion. Both told him the same story. The universe is ruled by law, and law points to mind. This dual vision is key to understanding him. Without the faith, his science might have lacked its urgency. Without the science, his faith might have lacked its rigor. The two threads wound together, hidden in part, but never separated. Newton saw himself not as rejecting religion, but clarifying it. For him, true worship meant uncovering the real order underlying both nature and Scripture. That order affirmed his conviction. Gravity itself was proof of design, evidence that the cosmos was threaded in rational law. Laws of motion and sacred text, each revealed in their own language, confirmed a creator beyond both. This was the private Newton, cautious but convinced, who lived within the margins of his own books. But the man who kept such beliefs in secrecy did not retreat into permanent isolation. In later years, he left the private study and stepped into public power, not as a mystic recluse, but as one of the most formidable officials of London. How did a man of solitude become one of the most feared officials in England? Newton, the thinker who once vanished from the world to chase equations in isolation, stepped suddenly into a role where power was not abstract, but daily and direct. He left the quiet of Cambridge and accepted appointment as Warden of the Royal Mint. It was not only a new post, it was a complete reversal of life. For the first time, his job was not to understand cosmic law, but to enforce earthly law with precision and force. The Mint at that time was no simple workshop. England's coinage was in chaos. Counterfeiters clipped edges from silver coins, melted old issues, and struck false ones with reckless ease. The result was a fragile currency and rising distrust in trade. And currency was no side matter. It was the backbone of the state's strength. Soldiers could not be paid, debts could not be trusted, and trade faltered when money itself fell suspect. Into this pressure chamber stepped Newton, already known for his rigor. Now his method would be tested on something far less forgiving than prisms or orbits. He applied the same habits of measurement to coinage that he had once applied to falling bodies. Each coin became a body in motion, every mark on the silver a sign to be analyzed. He studied weights, alloys, and striking methods with relentless detail. His records show careful inspection where others saw chaos. Every clipped edge or blurred stamp told a story, clues collected like data in a laboratory. Yet here the experiment was not neutral. Results could end with prosecutions and death sentences. Newton did not remain distant. He directly oversaw investigations, interrogating suspects himself. Imagine the scholar bending close, asking rapid questions, weighing answers with the same intensity he once devoted to equations. To counterfeiting rings he was not a theorist, but a hunter, gathering testimony, cross-checking, narrowing inconsistencies until the trap closed. When courts ruled guilt, Newton signed death warrants without hesitation. Coins on one end, gallows on the other, law enforced with unforgiving logic. This was no metaphorical gravity. These were chains, cells, executions. To modernize the transition from physics to policing feels startling, yet consider the consistency. For Newton, order was everything. In nature, that order was written in mathematics. In society, it was maintained by law and rule. A clipped coin and a violated equation both offended his sense of structure. Both demanded correction. His new post simply gave him state power to impose it. We see here another side of his personality, severe, meticulous, unyielding. Scholars who clashed with him in science had already felt his wrath in letters and societies. Counterfeiters felt it in courts under a regime where penalties were not fines but final. His pursuit narrowed crime to data, operations, presses, forgeries. Every fragment was measured. The contrast with his earlier seclusion is striking. Yet both lives shared a single root, the will to master disorder. His impact showed quickly. By enforcing reform of standards, removing worn coinage, and striking new mintages under strict weight, he restored confidence in the system. Trade steadied. The public once again trusted the tokens that passed through their hands each day. In this sense, Newton stabilized an economy the same way he had once stabilized physics. He gave firm law to spheres that had slipped toward chaos. Money itself gained reliability not by force of arms, but by the hand of a mathematician turned administrator. Visualize the tools of this new role. Where once he had notebooks filled with geometric diagrams, he now had trays of coins, scales for weighing silver, records of deposits. Ink still filled the pages he read and wrote, but the numbers carried lives behind them. A discrepancy in weight pointed to fraud. A duplicate die indicated an illicit forge. His new equations were balances of crime and proof, weighted until one side fell with certainty. And this work changed his standing. No longer a recluse tucked away at Cambridge, Newton became a public figure, deeply tied to government. He moved among officials, carrying responsibilities that touched the stability of the kingdom. His authority widened. This was not theory debated among scholars, but governance enacted daily in law courts. The man who had once mistrusted exposure found himself central to public survival. But his rise did not end at the Mint. In 1703, with his reputation solid, he became president of the Royal Society. In that role, he was not enforcer of coins, but of ideas. Once again, he commanded. He shaped agendas, determined disputes, and affirmed priorities. Through this institution, his influence spread across the scientific world. What he had once hoarded in notes was now the framework endorsed by the leading society of knowledge. Here again his character was evident. Rivals found no mercy. The conflict with Leibniz over calculus hardened in this period, and as president, Newton used influence to secure judgment in his favor. It was not enough to be correct. It was necessary to be acknowledged as correct, officially and absolutely. Reputation mattered to him as deeply as currency mattered to the Mint. Both had to be protected against dilution. Think of this as two stages of the same formula. First, stabilize the economy with honest coin. Second, stabilize science with accepted law. Both demanded vigilance, both faced fraud, false coins and false claims alike. Newton's method was the same: gather evidence, enforce standards, ensure order. Where others saw compromise, he drew firm lines. His life of paradox, secrecy paired with dominance, humility paired with severity, continued, but now under the bright light of public institutions, coins and death warrants, society charters, and published disputes. Newton held all of these as tightly as he once held geometric proofs. His shift from scholar to power broker was not accident, but extension. The logic of certainty and enforcement guided his every move. He left behind the orchard and laboratory, but never abandoned their core. In each new arena, society itself became the experiment and order the result he demanded. To this day, his tenure at the Mint shows us how broad a mind can operate. The same man who measured orbits stabilized a nation's economy, proving that reason and rigor apply not only to stars, but to silver. His impact extended from equations that guided worlds to policies that guided markets. Few thinkers cross from cosmology to coin, yet Newton did with the same relentless method. The isolated genius, once silent and hidden, became an institution unto himself. Warden of the Mint, Master of the Mint, President of the Royal Society, enforcer of order in both commerce and science. The transformation was total. He was no longer only the mathematician of orbits, he was a pillar of the kingdom. And yet his later years, despite this rise to power, would not be free of conflict. Old grudges and rivalries darkened his twilight, and mortality began to weigh as heavily as reputation. The man who once mastered his solitude would find no escape from time itself. What happens when the greatest mind of his age begins to fade? Newton had carried ideas from orchard to cosmos, from chalkboard to coin presses, from prisms to principles. But time does not spare even the most resilient of minds. By his later years he entered meetings slowly, supported by those around him, a man still revered but no longer quick with pen or proof. His life's work seemed nearly complete, yet his energy shifted from discovery to defense. The fiercest struggle in that fading chapter was not with an equation, but with a man he rarely faced directly. Gottfried Wilhelm Leibniz, another brilliant thinker, had also built the method of calculus, an idea we now know both men advanced independently, but pride, suspicion, and national rivalry transformed separate achievement into feud. Newton insisted upon his own priority, convinced that Leibniz had borrowed his ideas. Leibniz resisted, claiming original authorship. The dispute hardened. In younger years, Newton might have set dispute aside for work, but age sharpened his defensiveness. He returned again and again to documents, letters, and drafts, tracing timelines of discovery like a lawyer preparing evidence. His focus grew narrow, not a new law of motion, but proof that he had found the old ones first. It was an obsession with credit, with priority, with recognition that could not be shared. For a man who held secrecy since childhood, the fear of being overshadowed became intolerable. This contest spread across Europe. Scholars took sides. Articles and pamphlets appeared, each presenting arguments and insults. At the center, Newton coordinated from London, using his position as president of the Royal Society to shape outcomes. He wanted official judgment, not just private opinion. To him, only public confirmation of his priority could close the matter. Yet even as his influence secured favorable verdicts, his private insecurity deepened. Meanwhile, his scientific work slowed. In his youth, ideas had poured out, linking apples with orbits, colors with spectra, equations with law. In later decades, originality faded. Duties at the Mint consumed hours. Administration at the Royal Society demanded attention. Illness came and went. Writing grew slower, calculations thinner. The man once described as absorbed for days by single problems now spent as much energy defending as discovering. The rush of breakthroughs that defined his 20s and 40s no longer repeated in his 70s and 80s. Still, he remained a figure of awe. Imagine him entering a meeting hall. The frail body leaned forward, carried by attendants. Age had bent his form, but minds bent in respect as he passed. His presence alone held weight, like gravity itself, silent, unseen, but felt by every person present. He no longer commanded by innovation, but by stature. His survival into advanced age turned him into a symbol, the elder statesman of science, embodying a movement now larger than himself. That image hardened into myth on his death. In 1727 he passed away, ending a life that had stretched across revolutions of politics and knowledge alike. His funeral was no private ceremony. Dignitaries, scholars, and leaders gathered. His coffin did not go into simple ground, but into Westminster Abbey, a place where crowns and scepters rested. To enter him there was a choice that spoke volumes. His life was regarded with the same weight as kings, showing that reason and discovery had earned him equal place in national memory. It was an extraordinary signal for the time. Physics and mathematics rarely carried such honors. Yet Newton lay side by side with monarchs as though intellectual authority had joined political rule at the very highest level. His burial marked not only his death, but the rise of science into the center of culture. A thinker was now celebrated in the realm of kings, a measure of how deeply his ideas had rearranged the world. The question then comes, what mark did he leave behind? We can measure it not in monuments, but in machines. For centuries after him, Newtonian mechanics were the backbone of progress. The Industrial Revolution leaned upon his laws. Wheels and pistons followed principles of motion he had written. Engineers built bridges and engines with confidence in those equations. Astronomers charted skies using his gravitation. Mariners navigated seas guided by predictable orbits and tides. Consider rockets. Long before they rose from the earth, their possibility was imagined through Newton's third law. Every action has an equal and opposite reaction. Steam engines and turbines worked because energy transfers obeyed his second law. The spread of technology across the modern age echoed his mechanics line by line. His framework became the skeleton of our machines, the unseen pattern linking gears in a mill with satellites in orbit. Think of Newton's law of gravity as a spring stretched across the universe. Each body tugs on another, each motion explained by its tension. For generations, scientists pulled upon that spring with equations and found it held true. It was not until Einstein that limits appeared. Even then, Newtonian law remained accurate for nearly all practical uses. The satellites that orbit today, the rockets that leave our atmosphere, the calculations for flight, all trust Newton more than Einstein in daily measure. His framework is simpler, and for scales we live within, it works remarkably well. That durability is his legacy. Long after his disputes with Leibniz faded, after accusations and defenses died, it was the system of thought itself that endured. His name became shorthand for order. To be Newtonian meant to seek clear law, to measure with precision, to express motion in mathematical language. His physics were not just ideas, they were tools humanity kept at work for centuries. And yet, his life reminds us of complexity. In youth, he pursued curiosity with openness. In later years, he closed into obsession with rivals. The arc of discovery crossed into the arc of pride. His burial among kings reflected not only honor, but perhaps the solitary crown he sought, a need to be sovereign of ideas. But history remembers less the quarrels than the framework left behind. In the end, the laws outweighed the disputes. Newton's death closed one chapter, yet his influence extended unbroken. The centuries that followed were guided by what he measured. From the simplest pulley to the orbits of satellites, his fingerprints remain. Knowledge advanced beyond him, but seldom against him. His mechanics held strength until relativity and quantum theory carved new frontiers. Even then, those new theories began not by erasing Newton, but by building on him, adjusting, refining, extending beyond the reach of his spring. So when we picture the frail Newton at the end, carried to meetings obsessed with credit, signing documents with shaky hand, we must also imagine the other legacy, the one where engines turn, rockets launch, and planets orbit with predictable sweep. That is what he left. A world where motion became knowable, where law linked the falling apple to the sweep of galaxies, and it leads naturally to us. Because if Newton's era was shaped by gravity and motion, our own era faces mysteries he could not. Questions about dark matter, dark energy, quantum uncertainty, and the nature of consciousness remain to be answered. We stand where he once stood, at the limits of knowledge, the next launch pad prepared by those who came before us. Newton's legacy is not only equations, it is the reminder that one mind can redefine reality and that each generation has its own dragons of the unknown waiting beyond the edge of certainty. If Newton measured the universe, What mysteries remain for us to measure? That is the question modern science still struggles with. Newton explained falling apples and circling moons with laws we now teach to children. Yet, as far as those laws reach, they do not reach all. Today we face puzzles just as large as gravity once was, only hidden deeper in the fabric of matter, space, and even the mind itself. Consider what Newton gave us: order, symmetry, predictable motion. He taught us that equations could capture the sweep of planets and the push of machines alike. But when we extend that logic into the frontier of modern physics, cracks appear. Matter we can see is only a slice of what the universe contains. Beyond it is dark matter, invisible yet detected through its pull on galaxies. Beside it is dark energy, a strange driver forcing the cosmos to expand faster over time. Together these unseen pieces outweigh the matter Newton once measured. They are like weights pressing on a scale we cannot touch. Now imagine Newton alive today, holding his prism again. He would split light, but instead of colors, he would be told of wave-particle duality, electrons that behave as both waves and solid bodies depending on how they are observed. This is the puzzle we face in quantum mechanics. In Newton's era, the argument was whether light was particle or wave. Today the answer is, it is both, in ways that defy common intuition. Just as Newton's corpuscles once drew criticism, the paradoxes of quantum theory remind us the world is stranger than the tools we first used to examine it. Physicists now confront the measurement problem. At its core, the difficulty is this: why does a quantum system, spread out like a cloud, collapse into a single outcome when measured? The electron, which exists everywhere on its track, suddenly appears in one place. Some interpret this as the role of the observer. Others fold it into hidden mathematics still beyond us. It rivals Newton's own struggle to explain gravity acting at a distance. In both cases, forces appear to operate through gaps we cannot see. Shift to the largest of scales. Telescopes scan the faint glow of the cosmic dawn, the light stretching across time since the universe began. The picture is not balanced. Galaxies spin too fast. Voids expand too quickly. Something unseen makes up the difference. Dark matter binds structures. Dark energy pushes them apart. These terms are labels, not solutions. They mirror Newton's own fear of action without mechanism. He wrote of gravity that he could describe what it does, but not how. Modern science admits the same. We sense the tug of matter unseen, but the mechanism remains concealed. Other questions press even harder. What is time? In daily life we feel it flow, but physics suggests otherwise. Relativity teaches us that time bends, stretches, and slows, depending on speed or gravity. Some modern interpretations describe time as already complete, like a film reel where past, present, and future coexist. This block universe opposes our immediate perception, but fits the mathematics. If you were Newton, measuring seconds with pendulums, how would you reconcile with a theory that says seconds themselves may be illusions born from perspective? Step inside laboratories at the frontier. Particle accelerators hurl protons at one another until they shatter, revealing fragments beneath: quarks, leptons, bosons. It is an echo of Newton's own thought experiments, smashing light with prisms until its parts show structure. The difference is scale, from beams in a farm window to beams in vast tunnels. Both carry the same method: test nature by forcing it to reveal what lies inside. But questions remain unsolved. String theory suggests matter at its root is not particle, but vibrating lines of energy. Decades of development have yet to show measurable proof. Like alchemy in Newton's notebooks, it is pursuit without immediate return, a belief in hidden unity that has not yet yielded results. Some physicists still treat it as hope, others as misstep. Either way, it shows that the human search pushes beyond what experiments yet confirm, fishing in mathematics for deeper law. And still stranger ideas grow at the edge. Multiverse theories suggest our universe may be one bubble among countless others, each with different laws. The difficulty is evidence. As the research notes bluntly ask, how are we ever to prove that there are universes other than our own and that they are run on different lines? Without contact, proof remains beyond reach. It is parallel to Newton wondering how to measure a force he could not see. Gravity was inferred from motion, not touched by hand. Perhaps multiverse logic will one day follow the same path, inferred not directly, but through subtle markers left in cosmic structure. Questions are not confined to physics alone. Consciousness itself remains mystery. Brains are matter. Thoughts are experience. How do they overlap? Are they two sides of one fabric or distinct levels of reality? Science still struggles with this. The problem is not just mapping neurons but explaining why matter generates experience at all. For Newton, light and gravity were unsolved riddles begging to be expressed in law. For us, the riddle may be subjective awareness itself. If you were to plot the journey, it looks like this. Newton moved from falling objects to universal gravitation. We now move from visible matter to invisible forces, from seen energy to awareness itself. Each step widens the boundary of law, chasing hidden order through strangeness. His apple was simple, but led to cosmos. Our puzzles are deep, but may play the same role, pointing to a framework unimagined today. Think of it like peeling layers from an onion. Newton took off the first thick layers, revealing a system consistent enough to run centuries of machinery. We peel thinner layers now, each one harder, each yielding paradox. Quantum mechanics, relativity, cosmic inflation. These are sharp slices taken from inner rings. The onion still has core untouched. The hero's journey continues. Newton was the opening act, proving that measurement and mathematics could tame natural law. We live in the next act where measurement itself cracks, where observation alters outcomes, where the universe's mass is hidden. The scale of the unknown has not shrunk, it has grown, but the method persists. Question, test, reason, debate, refine. The courage that drove Newton is the same needed now. He looked at ordinary fruit and imagined galaxies. We look at faint starlight and particle collisions and imagine forces unseen. The challenge is the same, to bring what is hidden into the human world to write law where chaos seems to reign. If Newton measured the universe with apples and orbits, we now try to measure it with colliders and cosmic maps. The essence is unchanged. Discovery is not static. It is process, stretching past centuries, requiring minds bold enough to see unity where none seems visible. Newton's work was first chapter. The chapters since have grown stranger, but still turn one page at a time. And from here, the reflection is clear. Newton's influence endures not only in the laws we still use, but in the courage to face limits. His universe had edges. Ours does too. Each era inherits the same question: what lies beyond? Newton turned a falling apple into a universe of laws. What looked like chance became measure. What seemed ordinary became a system that powered centuries of discovery. Rockets and satellites still move along paths defined by those laws, carrying signals that link our world. His journey mirrors ours. Each generation faces mysteries that resist understanding, from dark matter to the puzzle of consciousness. Newton showed that patience, math, and experiment can pull order from confusion. One mind measured reality then. Today, it is our collective task to continue that measurement, pressing further into mysteries he never imagined.